All right, people on YouTube, please go do the quiz as well. So like I said, so I started the YouTube a little bit late. So like I said, I don't really have a way of making the quizzes feel not fake. But you know, we will have a technical question to one extent or another for the rest of the semester. And it's more like, like obviously people can look them up, like obviously. At the same time, I will be closing the quizzes at kind of about 1 hour after lecture. Like if you get it wrong, that would be an indication to you to get it right on the exam. It's not kind of to evaluate you. So that's kind of the compromise. There's some just logistical announcements. I have big plans that don't involve you for the weekend. So I'm going to a conference in Portland, so like tonight I'm flying out actually, and then I'm going to Palo Alto. It's gonna be, well, I don't know, like I think there's like a good chance that I'll be stuck in an airport somewhere in the US. I don't know. But anyways, so instead of the Monday lecture, we will have a Zoom session on Sunday, at noon Toronto time. So it will be aimed at people who want to catch up in the course. So like if you're feeling fine, then you don't necessarily need to watch it. The first part is going to be recorded. So this is going to be me continuing kind of giving advice, maybe being a little bit more concrete than today. I'll do a little bit of a thing today as well. And then I'll turn off the recording. And the plan is to just talk to people and give some, like, not exactly individualized advice. That would be for office hours. But if you feel like I haven't addressed kind of in my proposed plan, haven't addressed the issues that you specifically have with the course, you can bring it up and we can discuss it and come up with a plan that's relevant to you and possibly to other people as well. This will not be recorded, but it will not be like office hours. So there will be an office hour later where you can also talk to me individually, right? So a graduate approach. So also I arranged the thing with the people at Chestnut. So on March 31st, that's a Sunday, I'm challenging all of you to challenge me to a game of ping pong, and I will be donating 25 cents for every point that you score against me to the Toronto Humane Society. So, like if you like dogs and cats, you should come and try to score as many points as you can against me. Gonna be fun. So we have already some people signed up. I hope that they can play against every challenger. Like if it so happens that the entire class decides they either really like dogs or they really, want to take revenge against me for the midterm or something, I will prioritize kind of the first year Angsai students, and I don't imagine that there's going to be like more than 20 challengers, probably fewer. But if there are, I will try to prioritize you guys, and I will try to give everyone satisfaction. How about that? Okay. So that is this. I want to give, so I thought about just doing it on the Sunday, but I thought it might make sense to do it during kind of the main lecture as well, that people maybe don't feel that it's kind of optional to hear it. So one thing I want to say, there is no like one size fits all solution. Like, your individual learning plan should be in a way individual. So one option, and, like the TAs, for example, this week, a lot of the time we're just idling or just like making conversation, sometimes with each other. So there is an opportunity to go to the lab and just like ask a TA, like, can I show you my thought process? And can you maybe suggest some ways for me to improve? I think that could be useful. I encourage you to take that opportunity possibly next week. Of course, there's also going to be a lab assignment, but there are chances to do that. You can also come to office hours and do the same thing one-on-one with me. I might have some ideas. So again, I want to emphasize, I said it's, I think probably 5 times already this year, 2023, 2024. But again, like there's the only way to know where you are and the only way to know what you need to improve is to actually try to get code to compile, right? And then not just try, but get to the point where it does compile. I think it's a common thing that people learn in high school that, like in grade 12 calculus, like it's maybe true that if you like, just approximately throw something together and it kind of looks right, you get a 98 instead of 100, whatever, maybe you can still get into ANSI with a 98. Questionable, but maybe, right? So I think actually like most people have scored less than 98, at least last year. I don't know how admissions are going this year. But the average is actually, I don't want to quote numbers, but it's like not that far from 98 actually. But it is lower. It's not, so it can be like that with programming in the sense that if you are genuinely 98% of the way there, then yeah, like you should get a 98. But you don't have a way of knowing if you are 98% of the way there until you got to the 100%. Because if it's not working, it could be that it's almost there, but it could also be that there is some kind of fundamental misunderstanding or like you miss something really important that's going on, right? So please try to make things compile. Okay. If you can do that with kind of past labs, past projects, lecture examples, you're probably doing well. Like, and by well, I mean like probably you're getting an A or possibly an A+, right? So that's the main plan that I suggest to everyone is, just do the labs as if you're doing them from scratch without peeking at the solutions. It's fine to peek if you need to, but then go back and do it from scratch without looking. If you can do that, unless you happen to have photographic memory where you just like see the solution in your mind, there are people like that who just like literally like they can look and they remember the text verbatim. Okay, in that case, this would not work for you, but that's like a small minority. For everyone else, if you can, look at the solution and then rest for an hour, do something else, and then do it again, you know how to solve it. Okay. With that said, there are, I think, some people, not very many, but some for whom that's not a good plan. And those would be people who still need kind of basic practice in terms of just programming, maybe in general, but especially in C, right? So if you often find that you're struggling with like Q1, and some Q1s are not that easy, then it might be that what you need is just like basic practice, like the way when you're like whatever, like practicing for your fateful ping pong game against me, like you want to practice your serve first and not like start and trying to play a whole game, right? I should do that next week. In that case, you might benefit from doing the exercises from the first couple of chapters in the course one of the course textbooks in the King textbook. So the King textbook, I think I told it to some people individually, but not to everyone collectively. So the King textbook is the textbook that's used in APS 105. That's the first course in ECE. That's also the book that used to be used in ESC190 back when we taught ESC180 in the C programming language. So it's basically like a 180 type of book. And it might be good. Like if you need to catch up and if you need kind of the basic exercises, you can try to read it as well. To be honest, I think reading textbooks is of like limited utility for a class that's really skill-based, but some people could benefit from it. Doing the exercises kind of just like from the start, even if they look like they're very straightforward because like they're designed to be, it might help you in the sense that you develop kind of an automaticity that would help you when you are solving kind of the intermediate and the difficult exercises. All right. Again, super important to actually compile and test your code. Yes.
Back to the slide where you said you're doing very well if you compile code from scratch. Well, what does that mean? Does it mean that you're not looking up anything on the internet because you're not stuck on anything, or you can write code that runs in the first try?
Again, I'm not. So this is a conditional statement, right? So it says what's true is that. What's true is that if you haven't compiled and run it, then you definitely don't know whether you're doing well. That's all that I'm saying. And of course, kind of like it, and like you shouldn't take it kind of as gospel as well, right? So this is just a guideline. All I'm saying is that you can't just throw something together that you think kind of looks right and just assume that you're doing well. That's all I'm saying. Of course, kind of things really depend. Like you can't write like a complicated algorithm from scratch on paper and have it compiled. That just never happens.
So you're just saying you can't tell how your users cannot run their code?
That's right. Yeah. So what I'm saying is you don't know how well you're doing unless you're compiling, running, and testing. That's all I'm saying.
Okay.
All right. So okay, and like you might be doing well, like you might have a compiler in your head that's completely correct, and you don't need to compile with GCC, like you know anyways. Like there are people like that, but you don't know that you're like that unless you verified that the compiler in your head is the same version as the GCC compiler. It might be in incompatible versions, stuff like that. There might be bigger issues too. Yeah. All right. Okay. So, you know, the way the exam is designed, if you look at the first couple of questions, it's more about kind of just checking whether you've done what I just suggested, which is, you know, do like easy to intermediate exercises, try to compile them, make sure they run. And the first couple of questions are, in fact, like more than half, I think, are just designed to see whether you've done that. You know, whatever, like Q6 on the midterm was obviously not like that. It involved some problem solving, connecting some disparate concepts from the course. So connecting kind of C together with the first lecture that was about the ESC180 exam. So if you remember, like that question was basically like the same as what we discussed in the first lecture, except you needed to implement it in C, and you needed to say, oh, like, how do I store all the strings in one big block? In order to do that, you had to figure out, well, how large is the block going to be if I want all the possible passwords? How many of them are there? As we discussed, it's n to the k, where n is the number of characters and possible characters, and k is the number of characters in the password. So there's n to the k total characters that you need to store, depending on, you also need to store the nulls, stuff like that. How to get there? And the answer is, well, like part of it is it's problem solving. If there was a recipe, it wouldn't be called problem solving. However, again, kind of developing some degree of just automaticity with basic problems should help. So in the same way that the first step to being able to score very well on the calc exam is that you know whatever, that 6 times 8 is 48, and you don't need to think about it for 5 minutes and get it wrong. And how do you do that? Well, maybe you memorize the times tables. I never actually did, but I kind of have it mostly memorized just because, like, you know, in several points in my life, I had to figure out what 6 times 8 is. And I kind of remember, not necessarily because I memorized the entire times table, but just because, like, you know, like spaced repeated practice. I computed 6 times 8 multiple times. Last time I did it 60 seconds ago. You might have noticed that I paused a little bit to check that I'm right. So that would help. So at this point, I would also recommend Lead Code. So I'll post. So Lead Code is a website that people use mostly to practice for job interviews and stuff. So lots of job interviews basically, give you stuff that's from Lead Code. So I would say kind of Lead Code easy. The categories, I don't always agree with them, but I would say at this point, Lead Code easy are almost all legitimate things that you could practice with just for the ESC 190 exam. So medium, not necessarily. So like some medium are actually, to my mind, easy. Some medium, to my mind, are not that medium at all. So there, you kind of have to use your judgment, which is difficult. So I'll try to compile in the coming days, kind of some exercises that I do approve as like legitimate practice for 190. So part of it is that this gets to like starting to ask dynamic programming stuff and stuff like that. And specifically for dynamic programming, I think it's good, but there are techniques that we haven't covered that would also be considered medium, and that would not be covered. Yeah, again, those are of course optional. You should be doing project 2 and you should be doing next week's lab once it's posted. But if you want extra practice and you feel that you want like the problem solving rather than just developing this basic automaticity, that's where you should go. Okay. So one last thing that I want to say for now about practicing rather than doing new stuff, although that is kind of veering into new stuff territory. So like, look at this code here. So what was the point of showing it to you? So to my mind, there are actually several goals here that are served at once. So one goal is just, like you need to know how adjacency matrices are used in order to represent graphs. And to my mind, it's good to make it concrete with code. At the same time, for the vast majority of you, you haven't seen this kind of code a lot either, right? So this is something that we've introduced pretty recently, and then we're using this kind of in a sophisticated way. You probably, like, you all have done project 3 in 180, so you hopefully kind of remember how dictionaries can be used in order to kind of associated objects with strings. That's what project 3 in ESC 180 was all about, but it was kind of a reminder of that. Plus, it was an example of putting it all together. So when you're studying this kind of code from lecture, what should you do? So here's my suggestion. Try to compress it in your mind as much as possible, right? So kind of just say, okay, if I need to know about this, what's like the smallest amount of text that I can write if I had a cheat sheet that I could just look at it and I would reconstruct this code. This is actually like how I would study for undergrad exams. So what I would do, and you don't have to do it, but something that worked for me like reasonably well. So I kind of made kind of pretty extensive notes. So I would say usually like 10, 20 pages, depending on the course. And what I would do is I would write down everything that I didn't know and didn't understand, right? And, like if I wasn't paying attention in lecture a lot, it would be possibly 30 pages. If I was paying attention, I wouldn't have to write down as much because I could just write a little bit and I was sure that, okay, like if I look at it again, I could reconstruct the entire thing, right? And then I would like compress it more and more until I would get to like 3 pages that I literally, all I could do with that material, the 3 compressed pages, I could just memorize. And that is what I would do. So I lived in North York, so I would like, take my 3 pages, memorize them on the subway, and Like sometimes I would come, like for some stuff, I would be like, okay, I do not have deep understanding of it. I'll literally memorize it and I'll literally like sit down when the exam starts and I'll just like write everything down that I need to know that's fresh in my memory. And then I would use it as a cheat sheet, which is allowed. Like you're allowed to use your brain as a cheat sheet, right? So I think this kind of approach can be useful here, right? So here's how I would approach this, I think, and it might be different for different people. Like the entire point is you decide for yourself what it is that I need to know in order to be able to reconstruct this code, right? So I think what would happen kind of in my mind here is I would write down something like this, at least at first. And then I would try to compress it more and more as I kind of internalize the information, right? So I think I would say at first, like, okay, like what's an adjacency matrix? And I would say like Mij is 1 if nodes I and j are linked. I would not write down 0 otherwise. So kind of trying to write down like the easiest nodes possible. And now let's say, okay, so how do I represent this? So like this is like probably not really enough, right? So like I would say like nodes can be airports. And I would first maybe write examples and so on. And then I would say, like, this is like, if you remember, this is index 0 and this is index 1. They're in reverse order for some reason now. And this is 3. And I would maybe make a little picture here. So I would say, like, okay, so like white horse. Oh, thank you. That's because on the exam you can't. So that's because it's like, thank you. So so I would say like white horse 0, and I would say YUL 1, and I would probably not continue here. Horse. And I would put a 0 here and a 1 here, and I would put like a 1 as an example. So in the second iteration of my notes, I would probably not include that. And here, kind of the key idea here in terms of mapping is that I have a dictionary that maps the strings to numbers, right? So I think I would write it as like nodes dict, and then I would do it with an example. So I would just say like YYZ is equal to 3. Right? This I would not add. And then maybe I don't think I would write it down in the first iteration, but like R, YYZ, and YUL linked. And I would write it as like nodes dict. So I have so this is one index, and then this is the other index. So I would write it for, well, like you look up the index for YYZ and you look up the index for YUL, and then you say, is it 1 or is it 0? Right? So I feel, again, kind of it might be different for different people. I'm kind of pretending that I don't know this and trying to reconstruct kind of like, if I take one step back from before I learned this, what would it look like? I think to me, it would look like this. It might be that you need to elaborate more as well, at least at first. And then I would just remind myself, so average case access for Dix is O of 1, but worst case is O of n. And then I would say for list is O of n because you need to go through the whole list to match the input. So this kind of code, I think if I didn't really remember how to do it, initially I would also include it in the notes. So I would say, okay, so this is what it looks like. And then I would remind myself how to make a graph. So if it's a list of nodes, it would be like node YYZ, node YUL or something. All right. So if you remember, in order to make it efficient, they kind of use nodes there. So I think this would be kind of like my first stab at trying to summarize it. So, you know, like you might ask, like, why don't I do this? And the answer is, well, sometimes I do. Like, that's kind of what the slides look like. Part of it is that, you know, it's different for every person, kind of what's salient to them and kind of what's completely automatic to you. So like, if this is enough for you, then you don't need anything else. But it might be that you have another issue with the code that you don't completely understand, where at first the notes need to be more elaborate. And I think like I could write the notes, ChatGPT could as well. In fact, you could try it. But really the utility of the notes is that you arrange the material in your mind so that you can then compress it so that eventually, hopefully, you get to the point where it's two or three pages that you can memorize on the subway. You'd have to take the long way from if you're going from Chestnut in order to memorize it. But yeah. So, okay. So I think kind of doing this kind of thing can be useful. And I think one kind of common thing that people do that I think is not that useful is they try to memorize the code, right? So I'm not saying it's not better than nothing. It probably is. So like you can probably kind of pattern match in the exam and kind of get something. But to be honest, like especially in the age of ChatGPT, like if you're doing that, you're like probably strictly worse than ChatGPT at that. So it's not really useful long term. And it's not a strategy that I think would allow you to do all that well on the exam. So I think kind of summarizing it and compressing it more and more so that you can say eventually, okay, like I just need the 2 pages that maybe I don't fully understand, but I just memorized them. I think that that's kind of a good strategy. So it worked for me, although I should say like my undergrad GPA wasn't like anything to write home about. So maybe you, so like a lot of you have better GPAs. So like maybe you have better strategies. So, okay. 4.0 in grad school though. So, okay. It is easier in grad school. So, all right. So with that, I want to go on to a more complicated algorithm. So this is called graph traversal. So to traverse just means to go through something. This is also on the exam, by the way. So we start with with this kind of graph, and maybe it's represented as an adjacency matrix. maybe it's this bunch of linked lists, and we want to go through the graph, and we want to basically print every vertex at least once. Sorry, also at most once, well, just once. So what's the strategy that you would generally use if you just had to do it? So if it's like a graph that fits on one page, you could just say, well, like I just graphically, I'm going to look at it and I'm just going to write whatever. Like, I'm just going to go like top to bottom, left to right or something, right? So you can do it. Just say whatever, like 7, 9, 1, 2, 3, 8, 4, 6, 5, right? If you imagine that this graph is very big, and in order to go between the nodes, you actually need to do something. So, for example, you are Google and you're indexing the internet, right? So you want to like print out all the web pages on the internet. How would you, or the address it? How would you do that? Well, you'll start with some starting points, and then you would go to every link. And then you would go to every link at every link, and so on. Does that make sense? So that is how I want you to think about it. Like we're trying to print out all the addresses of all the internet pages, right? So how can we do? Yeah.
Is there like a standard for storing values in a graph in some sort of order? So if we want to start the list at the end, it's easier to do it that way.
Yeah. So the question is, so this is called like some kind of canonical ordering. And the answer is, well, no, graphs are inherently unordered, right? So it might be that you want to print everything in alphabetical order by value, right? But the values in the nodes are not the same. Like those are just you can think of them as just like the names of the nodes, right? So you might say, I want them to be alphabetical, but that would be an arbitrary decision. So here, like you can start from anywhere. And in fact, Google doesn't know where to start indexing, right? The best it can do is it can just say, well, like I'll start with like this set of web pages that I decided on, and then I'll crawl from those pages further, right? There's no inherent ordering to those. Like it's whatever happens, happens. So how might you do it? So one thing you might do is you might say, okay, I'm starting at 1. It so happens that I'm starting at 1, and then I'll just visit this guy and I'll visit this guy because they're connected to 1. And then once I've visited 1's neighbors, I'll jump to the first neighbor that I've visited, so 3, and I'll visit 3's neighbors, right? So I'll go to 2 and I'll go to 4. Okay, so once I've visited 3's neighbors, I'll visit 6's neighbors. So only has the one neighbor that hasn't been visited, that's 5. And now I'll visit the neighbor's neighbor's neighbors, and so on. So eventually, if you visited the starting node, and then you visited its neighbors, and then you visited the neighbor's neighbors, the neighbor's neighbor's neighbors, and so on, you will have visited everything, assuming that the graph is connected. If the graph is not connected, you're in trouble. So if there is another component there, which is not at all connected to 1, if you don't have a seed web page that's in that component, well, you'll never get there, of course. The best you can hope for, if your strategy is to just hop between web pages following links, is that you start with enough web pages that they're connected to everything. It's very possible, in fact, it's true that, whatever, like, so like North Korea would be an extreme example, but they apparently have like their own internet that's like not linked. So anyway, okay. So here is what I said, but written in pseudocode. So what we'll do is we'll see if there is any neighbors that are not visited, and if there's no one's neighbors is unvisited, then we're done. So that's the while. So now what we'll do is will keep track of nodes that we visited, but whose neighbors we have not yet visited. And we'll store them in a DS. So DS would be a data structure, and it could be different data structures. Depending on which data structure it is, it would be different. So what we'll do is we'll put the next node up in the DS, and we'll say, okay, like we just put you there and now you're visited. And now what we'll do is we'll keep taking stuff out of the DS. Once we've taken it out, we mark it as visited and we add its neighbors to the DS. Okay, so let's do it with this guy. So speaking of strategies, right? So what do you do with this kind of algorithm? I think initially what I would do is I would just write it down and maybe say, okay, this is the kind of thing that I got to memorize. I think once you get the intuition for it, which maybe will happen in the next 9 minutes and maybe not, you might start just saying, okay, I remember it, or I just need like a small reminder. So let me kind of try to reconstruct it. Let me move this here. Yeah. So, okay. So I have my DS. And initially it's nothing. And this is for okay, that's what the DS is for. And I'm calling it the data structure. Later on, kind of a spoiler, it's going to be maybe a queue and maybe a stack and maybe a secret third thing that we haven't covered yet. So, okay. And what I'm going to do, so let me first do it kind of just intuitively. So I'll put 1 here. And then I'm going to say, keep right? So I'm saying while DS is not empty. So take out n from DS. Right? So let's run this. So we started by putting 1 into DS. And what I want to do now is I want to take 1 out. So 1 is now visited. And now every node that's not visited, I want to add. So the neighbors of 1 are 6 and 3. So I'll put in 6 and 3 in some order. Again, to your question, there's no canonical order, whatever. So like if it's a linked list or something that stores the neighbors of 1, well, it's going to be probably in the order in which it's stored in the linked list. So 6 and 3. And now what we're going to do is we're going to say, okay, back. So DS now has 6 and 3. So I'll take 1 element out of DS. So 6 would be taken out and would become visited. And now I need to see which neighbors of 6 have, oops. So which neighbors of 6 have not been visited. So 6 has one neighbor that has been visited and another neighbor that hasn't been. So 5 has not been visited yet. So that would be added to the DS. All right. Okay. So now it's 3's turn. So you'll notice that my DS is a Q implicitly because I'm taking out from the left and I'm adding to the right. So 3 would be taken out and will have been visited. And now 3 has 1, which has been visited, 4, which hasn't been visited, and 2, which hasn't been visited. So 2 and 5, in fact, as well, which has been which is already in the DS but hasn't been visited. So we got to add it now as well. Although, well, we'll check if it's in DS too. So we'll just add 2 and 4. Okay, and we'll keep doing it. So now we added so we added 2 and 4, and now it's 5's turn to be visited. So 5 is going to go on the visited list, and now 5's neighbors are 6 visited, 3 visited, 4 in the DS, 2 in the DS. So nothing more to do. So then we'll take out 2. That's the same thing. And so on. Right? So what we keep doing is we keep kind of exploring the graph, and every time we visit a node, we say, if your neighbors haven't been accounted for yet, stick them in the DS to visit later. And that way, eventually, everything will have been visited. All right. So there is an interesting thing to this, which is that depending on whether the DS is a stack or a queue, you'll get different orderings, right? So imagine that DS is a queue. That's what we've been doing here. So if DS is a queue and you start with 1, what's going to happen is you're first going to visit 1's neighbors. So you're going to visit 3 and 6, because when you're visiting 1, you're saying 3 and 6 are next up in the queue to be visited. Just think about it as a physical queue, right? So like put 3 and 6 in the queue, they're going to be visited first. And then when you visit 3 and 6, you're adding 3's neighbors and 6's neighbors into the queue, but those will be visited after 3 and 6. And then their neighbors will be visited. So you can think of it as first 1 is visited, and then whatever is like this 1 hop distance from 1 is visited, so like 3 and 6. And then whatever is left, that's 2 hops away from 1. So that would be 5 of 2 and 4 and 5. And well, at that point, we're done. But you're basically listing 1 things that are 1 hop away from 1, things that are 2 hops away from 1, and so on. On the other, so this is what's called breadth first traversal. This means that you are kind of branching out right away. On the other hand, if you make one small change and you make DS be a stack, what does it mean? It means that the last thing that you added to the DS is the first thing that you're going to visit. So we're going to go over it in more detail, I guess, next time. But the basic idea is, okay, like you visit 1, so you add 6 and 3 and 2 to the stack, and then you pop something off the stack. For example, you pop 6 off the stack, and you say, okay, 6 is visited, now add 6's neighbors. And 6's neighbors now have higher priority than 1's neighbors because they got there last. So they're going to go out first. So that means that you go from like 1 to 6 and then to 5 right away. Right? And then you don't go to 1's neighbors or 6's neighbors, you go to one of 5's neighbors. So you go like 1, 6, 5, 4. And then you don't go to 1, 6, 5 neighbors, you go to 4, you go to 4's neighbor. So 3 finally got lucky, even though it was 1's neighbor to begin with. Now it's going to get visited. Actually, well, in this, because like we decided like 1, 6, 5, 2 actually, and then 3. So that is wrong. So what I said is right. So that's called depth first. The idea is you're going kind of as deep in the graph as possible, as early as possible. So we'll repeat that later on. Okay, I will see you on Sunday at noon. If you're coming to Nocturne, I hopefully be there as well. See ya, bye.